Gentlemen, welcome to the workshop once again. Today we have on the bench a Taramps Base 5K. This is a pretty rough and ready monoblock amplifier that actually produces 5000 watts RMS into our 1 ohm load. It's using pretty modern MOSFET technology, nice low RDS, high speeds, Class D switching, and nice thick board traces, etc. It does make the power that it claims. However, this one doesn't make any power because it doesn't work. Let's have a look at what it does. Before we give it any power, we're going to take our multimeter here and just confirm that there are no shorts on the output section or on the power supply. So if we go across the power supply, there's no short there. We're just charging up the capacitors, so that's good. No shorted power supply FETs. Let's check the output FETs on this side. No shorts on the low side, no shorts on the high side. Check this side, no shorts on the high side, and no shorts on the low side. So we have no shorted output or power supply FETs or anything like that. So let's go ahead and turn on the power supply. We're going to allow about 7 amps in to start with a 12.3 volts. So let's first of all probe the power supply MOSFET drain, and what we should see on the scope here are a couple of pulses for health check mode, which is going to just build a little bit of rail voltage, and the amplifier is going to make sure that everything is a-okay. Rail voltage is building. The DC across the speaker terminals is equal because it uses a single positive rail, so there's half rail across the speaker terminals at all times, so it needs to make sure that's equal. So let's hit it and see those pulses. There we go, that's what we want to see. And then the duty cycle is going to increase once it decides that everything is a-okay. The duty cycle increases to just below 50%, build full rail voltage. Then it stays on, but then it goes away. Okay, let's have a look at that again. Health check mode, it decides everything's okay. Duty cycle increases, building full rail voltage, and then it should power up and stay active. However, it goes off. Okay, let's now take a look at the output section. What we want to do is probe one of the low side drains. That's where we'll get our Class D switching appear, provided this amplifier is a-okay. So let's power up again and see what we get on the scope screen here. Okay, not getting anything at all, just that kind of first initial bit of DC that will then become half rail once the Class D switching initializes. Let's check the other side over here, see if we get any signs of life from the Class D circuit over here. No, nothing on that side either. So the amplifier is detecting that there's no Class D switching happening, and it's going into protect as a result of that. So what we need to do is turn our attention to the output drive circuitry, auxiliary supply voltages, and stuff over here. So the drive IC that this Class D circuit is based around is the IRS20957S, and with this being a full bridge amplifier, we have one per channel, if you like. It's kind of 2 channels, but they're internally bridged at all times. So this chip provides high and low side drive to the MOSFETs, and you can bootstrap the high side. It has programmable dead time and a few other features like that. So the fact that we've got no Class D switching might indicate that there's a problem here with the supply voltages to these ICs. Now, supply voltages to these ICs are provided by this 12 volt regulator over here, 7812. That gets probably somewhere like 18, 20, 25 volts from a little circuit over here, generates some pulses, and then we get a steady 12 volts out of that, and this actually supplies power as well to the preamplifier circuit over here. Got some op amps, and these op amps, rather than using a bipolar supply, they're just using 12 volts and then a floating kind of midpoint ground, and then 0 volts as the negative supply. So we want to go ahead and make sure that we have power at the regulator. So let's turn the supply back on. Input, we have 23 volts, okay, and the output we have 12 volts. As you can see there, 23 and 12. What is interesting to me, however, is that when we remove the remote from the amplifier, I'm probing the 12 volt output from the regulator at the moment, we still get 9 volts. So with the remote applied, we get 12 volts. With the remote not applied, we get 9.7 volts. Now, it's been a hot minute since I worked on this exact model of amplifier. This is actually a slightly older base 5K from Taramps, and I don't think that that should be intended operation that we have, because that's basically going to be supplying 9 volts with the remote removed to the 20957S chips, and that's going to keep them alive. And we can actually confirm that if we have a look at these chips themselves. Take it to the datasheet real quick. This IC will provide a 5 volt reference, so it's a kind of a little internal regulator. So there'll be 5 volts on pin 6, which it generates itself, and that will provide a reference voltage for the OC set pin over here, and you can then put a resistor in here to change the overcurrent setting. So if we get 5 volts on pin 6, that means that the chip is powered and active through VCC. So probing pin 6 itself with the amplifier off gives us 5.4 volts. Okay, we actually have a little bit of noise on there, little spikes there. Let's hit the remote and see if that cleans up. Okay, so no, with the remote hit, that stays exactly the same. Nothing changes about that reference voltage as we apply and disapply the remote. If we go over and probe the inputs, you can see here that that's going to be tied to the regulator. So yeah, we get 9.7 volts with the remote not applied, and then as we apply the remote, it jumps up to 12. Doesn't seem like intended operation to me, but let's continue digging further and see if we can find out what's going on here. Another thing we need to check is whether we have VDD on pin 1. Take you back to the datasheet. This chip needs a supply voltage on pin 1, and that is the supply for the input side here, referenced to VSS, which is usually grounded in these amplifiers. So I'm looking for, I don't know, somewhere around about 9 volts probably on pin 1. So with the remote off, we get 9.4 volts, and with the remote on, we get 10.3 volts. So that's still active as well, even with the remote off. So we seem to have all our supply voltages present, even though they remain on when the remote is off. I'm not sure again if that's intended or not at this point, but we have all our supply voltages. So why aren't we getting Class D switching? Well, take it back to the datasheet. You can see here that we have pin 2 CSD. Now that needs to be high, if I remember rightly, for the chip to be active. So we can probe pin 2 and have a look and see whether it is high or low. Pin 2, power up the amplifier. We're low at the moment. It should jump up high. Okay, it stays low. Now the 20957S will pull pin 2 high internally, so the fact that that is low means that it's being pulled low by some other circuitry on the board here, likely controlled by the MCU. This is a programmable chip, programmed with firmware at Taramps factory, and that will deal with protection, startup health check, and a few other bits, power supply, PWM. So this chip believes there's a problem due to probably one of its inputs is high or low, and it shouldn't be, and that is preventing the CSD pin from going high, and that's this little circuit right here that's responsible for communicating or pulling pin 2 low if some other parameters aren't satisfied over at the MCU. Now we've already checked the output FETs are not shorted, doesn't really seem to be any damage. I've done a visual inspection, everything seems okay. I've actually gone through and confirmed that there are no obviously shorted semiconductor parts like these big diodes, glass diodes, etc. Nothing standing out as being obviously bad or faulty. So one last thing to check before this gets interesting is, you can see here, pin 3 is our input, and that needs to be in PWM form, unlike the 2092, which can take audio sine wave input on pin 3, I think it is. The 20957S requires PWM. It requires the audio wave to already be converted into PWM. So we're going to have a look and see whether we've got any PWM on there. So pin 3, let's have a look. What do we have? When the remote is initially applied, we get a little bump up, and then it's flat again. Now we're going to check the other side, because this is a full bridge amplifier. We should get maybe the exact opposite behavior over this side. Yes, we do. We get a little bump and then it stays high. What I'm going to do is inject some audio, okay, some signals, a little bit of RCA signal, maybe like 50 Hertz or something like that, into the RCAs here. Turn the levels down a bit on the side, and because obviously the preamp circuit is all alive, we might get some PWM, provided that circuit's all working, on pin 3. If we do, then we know that there is a problem, an issue with the protection circuit, and it's shutting the output down unintentionally. But if we don't get any PWM on pin 3, then I think we have a problem with the PWM generation circuit in converting the audio waves into Class D pulses. So I've just got a little bit of signal going in now, and I'm going to probe pin 3 here, being very careful not to short anything out. We're going to zoom out a bit on the scope to about 5 milliseconds divide. That will show us our 50 Hertz hopefully if we get high enough signal. Let's turn the amplifier on and see what we got. Okay, there we go. So yes, we do in fact have 50 Hertz PWM on pin 3. Let's just check that on the other side as well. Yep, there we go. So we do have PWM making its way to the drive IC. So we have what looks to be a protection circuit fault here. The amplifier is shutting down for what seems like no good reason. It is still possible that one of these drive ICs is faulty. It could be internally damaged, and it might even be pulling the CSD pin down low. And that one will then, because it's tied to the other one, the CSD pins are tied together through this circuit, it will pull the other one low as well. So what I'm going to do is actually disable the protection, the shutdown, and what that means will happen is that the second the remote is applied to the amplifier here, even when the rail voltage is at a very low level, maybe like 5-10 volts, if we lift part of this circuit to allow the CSD pin to be pulled high immediately, then these chips will spring into life and start trying to switch the output FETs, which is what we want, because that will happen at a very low, safe rail voltage before the PWM on the power supply side has gone full duty cycle, and before we have scary high voltage in the output capacitors here. So all I need to do is have a look at my power supply up here, and I'm going to turn the current way down to maybe like 0.5 of an amp. That means that when the amplifier tries switching the power supply FETs with that sort of very low duty cycle pulses, it won't be able to actually build much rail voltage at all, because there's no current on tap. But there will be enough current still in the board to run the output drive circuit and stuff like that. So that's how we're going to do it. But in order to get that set up, we need to go ahead and disable that shutdown circuit. And if we take our multimeter here, let's just discharge the rail caps so we don't accidentally short anything out. I'm going to take a 16 ohm load here, put one on the case ground and the other one on this rectifier output. Nice little spark, and a tick sound means that these three capacitors have been safely discharged. So let's grab the multimeter and start probing back where the CSD pin connects to in the circuit. So pin 2 of this, let's just confirm that it is paralleled with the other one. Yep, so both these chips have their CSD pins connected together, and I believe they connect through to Q4 here. And we have a resistor here as well. Anything else directly connected? No, it doesn't look like it. So I'm trying to remember off the top of my head, I believe that Q4 will pull this pin down, and this resistor, I can't remember exactly which one it is, but I think we need to remove Q4. I don't have schematics for these amplifiers. I could probably get one, but I don't really need one. It's all very simple. You can just follow stuff back. We've got the data sheets. It's quite simple to work on. So let's turn on the hot air gun, remove Q4, and see whether that allows pin 2 to be pulled high internally. Let's wait for the hot air gun to heat up a little bit. I've got this big long nozzle, which is fantastic for getting into tight spaces and great for videoing because it gets the great big thing out of the way. But it does take an extra minute or so for this nozzle to actually get up to temperature, because obviously before then it acts as a cooling pipe and it just cools the air that's coming out the end as it gets up to temp. So let's just give it a minute. And I can actually use the slightly cooler air that's coming out to preheat the board around it a little bit. It's not too much of a problem with these boards. On lower quality PCBs or thinner boards with less thermal mass, you do have to worry about popcorning or blistering the board if you heat one area too vigorously without preheating the rest of the board. You get the air underneath or sandwiched in between the layers, it expands and it creates this bubble pushing the top layer of the PCB upwards, which is definitely not what you want. So always a good idea to preheat the boards. But these are actually very well built amplifiers with really good quality PCBs, very thick, loads of thermal mass. I've never had any issues with popcorning on a Taramps board before. Okay, I think I can see solder starting to melt a touch there, so let's get the tweezers and see if we... Oh yes, there we go, lovely stuff. So let's just pull that off and pop that to the side for a minute. Now the power supply we have turned down to 0.5 of an amp. Yeah, I'm just going to leave it at that for a sec. And I'm going to probe pin 2. I just want to see whether it rises at all. That's interesting. Pin 2 is now sitting at 9 volts. What we got on the output FETs? Nothing. Okay. That's because we don't have any PWM on the input. I don't believe that this behavior is correct, and I'm going to probably go hunting for why most of this circuitry here is up and running with the remote not even applied. But nonetheless, let's apply the remote and see whether, because clearly that's made a difference. Now we have some DC on pin 2, 9 volts there, so this might spring into life if we apply the remote and give it some PWM. Let's probe the low side drain of this channel. And actually I think that the amplifier would probably start switching at this point, because everything's up and running. The drive IC is up and running, CSD is high, the only thing missing is a bit of rail voltage, I think. So let's give it a touch of rail voltage and just see if we get any PWM on this low side drain. Yeah, oh what the hell? We do in fact get some PWM on the low side drain. There's not quite enough current there to actually lift it up a bit, so I'm just going to go ahead and turn the current up to about 1.5 amps here. Let's see if that gives us any more current. There we go. So I do still have 50 Hertz going in, so I'm going to remove the remote. I'm going to remove the RCA just to allow it to self-oscillate if it can. Oh, there we go. It just momentarily there, I just got a lot more Class D switching going on. What was that all about? What did I do differently there? Okay, because we're running on such low rail voltage, Class D amplifiers don't like really being powered up or idled without a load across the speaker terminals. So I'm going to dump my 16 ohm load across the terminals real quick, and the reason for that is that the filter network here often relies on there being a load across the speaker terminals to operate as intended, to actually filter and present the correct kind of loading and resonance to the output FETs as intended. So I'm just going to shove my 16 ohm load on the terminals for a moment here, and let's have another look on the scope and see what we get. Probing low side drain. Okay, well we definitely have something different. Hey, there we go. Yes, Class D switching is looking good. I'm just going to pause the scope on that for a moment. Let's have a look at our rail voltage. We're up at wait, how are we up at 45 volts already? Oh, that's because I was still letting 7 amps into the board. Let's just wait for that to dissipate. But interestingly, that was actually switching, but I want to just reduce that a bit. Ah, yes, here we go. We do have some Class D switching, and you can see here that the initial pulses from the power supply FETs build a little bit of rail up to maybe like 10-12 volts there, and then the amplifier goes into protect, but because the output section is still alive and the CSD is high, we get Class D switching over here remaining until the rail voltage dissipates. I'm going to turn the current up a touch so we can get a little bit more rail on there. There we go. So we're up at 20 volts rail, and that appears to be switching nicely. Let's check the other side of the board over here and see if that's the same. Yeah, it is. That looks great as well. So we can see here that yes, the output section is capable of switching perfectly fine. It just is not happy about something, so it's in protect for not the correct reason, and it might have something to do with the stray voltage being present with the remote being off. I'm going to investigate that. Now I know that it definitely can Class D switch. Everything seems okay. I think what I might let it do actually is I might just let it. Shall I let it go all the way up to full rail and just see if it can maintain switching right up at full rail. Let's turn the current up to 4 amps here. Gonna let it climb all the way up. Yep, we have 1.3 amps. We are switching at 60. Rail voltage is currently sitting at 91 volts, and we have, yeah, nice Class D switching on that side. The amplifier is now actually powered up beautifully. We're not in protect anymore. So yeah, the amplifier is perfectly fine, capable of operating, and interestingly, it does actually shut off when I remove the remote. We now only have 6 volts on the output of the voltage regulator with the remote removed. We don't have VDD anymore with the remote removed. Let's check pin 6 for 5 volt ref. Pin 6, we do still have 5.3 volts, so a lot of the circuitry is still active, but it has changed a little bit in its behaviour. I'm just going to go and hit that again. So yeah, Class D switching, everything seems good. Switching at 100 kilohertz, pretty much on the nose. That's about right for this amplifier. So yeah, everything seems fine. Class D switching initializes and disappears perfectly fine. Let's check on the speaker terminals. we get half rail, which is, well, thereabouts. We get 40 volts on the speaker terminals for the sine wave to swing up and down, to and from. So yeah, perfect functionality. Just won't do it by itself. We have to force it. So I'm going to let the rail voltage dissipate, and I'm going to investigate some of the circuitry around the protection modes and the CSD here. Right, I've been doing some reverse engineering on the circuit that supplies voltage to this regulator and so on, and it appears that yes, in fact, it is a design choice to have a lot of this kind of circuitry active even when the remote is off. We have 12 volts sitting on this diode right here and here, and it kind of goes through this diode here to this diode here, goes through this one and sits on there, and same goes for this. So yeah, we do have the 12 volt from the terminal connected through to this regulator and the output drive ICs at all times, regardless of whether the remote is applied or not, which is interesting. Anyway, with that out of the way, let's turn our attention to this circuit then. So you can see here Q4 is supposed to pull the CSD line low, because we have CSD here on this pin of the transistor, we have ground over here. So when this is high, this is going to make a connection between these two and connect them together. So if we probe this pin, which is probably coming from the MCU, we can see how it's behaving. Now we don't have this transistor fitted, so the amplifier is going to work, and as we saw earlier, it's going to come to life absolutely fine, and the MCU is going to be active, blue LED, and it's going to function. So I'm going to turn the current back up again, and we're going to let the amplifier come into full operation and stay on with a blue LED, and I want to see what does pin 1 of this transistor thing do. Does it actually go low, that would enable the drive ICs to remain active, or does it stay high, meaning that there is an issue there with that circuit? So let's go full power up and get some Class D switching rolling again. There we go, we're coming up nicely. And we have a blue LED, and the fans come on. So the amplifier is happy and functional. So let's zoom in on these pads and see what we got. So when I first apply the remote, this pin 1 should go high, pulling CSD low, which it does. What does it do when the amplifier decides it's okay? It goes low. Okay, so that's behaving as intended. Well, that's curious, strange, and interesting. Another thing I've just noticed is off camera, unfortunately I didn't catch it on camera, when I first powered this amplifier up, you can see these 3 LEDs. You've got blue, orange and red, and when I first powered this amp up, when I initially got it testing, the red LED was very, very dim, and it didn't have the full voltage on it that it's supposed to. It only had about 1.8 volts instead of about 2.5. However, with this transistor lifted and where we've been poking around, this red LED now is lighting up as intended. I'm wondering whether there was a tiny strand of copper wire or some conductive. You can see this amp is very dusty, and it's been in the back of a diesel with the boot open, so a lot of this black dust is kind of probably a little bit conductive. We should probably clean it out. What I might do is just fit this transistor back in place, give it a good clean up, and just see if it starts behaving. If it does, then we'll know it's just conductive nonsense or something in here that we have rectified by poking around. Just drop that nicely back in place. And let's just try and give it a general clean up. Like, it's not too bad on this area of the circuit, but it's a bit janky over here by the speaker terminals, for instance. Actually, one of the only things I can think that I've got differently to how I initially powered it up when this red LED wasn't working is I've got a wire connected here across the speaker terminals, which I didn't have when I first powered it up. Now that shouldn't make any difference, and if it does make a difference, then you've got a fault with the amplifier somewhere you need to identify and resolve. But that's the only thing I can think of that's different about how it is now versus how it was when I first tested it. I mean, this is disgusting around here by these output FETs here. Oh, this is horrible. I don't know if I've got anything small enough to really get in there. What this could really do with is a carbon clean. But unfortunately, my repair business isn't lucrative enough yet for me to warrant a ultrasonic cleaner. Did I say carbon clean? I've got my head's in diesel land too much, because this is the guy was saying, oh, it's going to be covered in diesel smoke. This needs an ultrasonic clean, good ultrasonic clean, not a carbon clean. But yeah, they're pretty expensive, and to get one big enough for the kinds of larger boards that I work on, I mean, this isn't working on phones and laptops here, it's working on pretty big boards from large amplifiers. I would need a fair sized one, and don't really have the space here either. The workshop's pretty small, and generally it's not needed, just for kind of edge cases like this, or ones that are heavily water corrosion damaged and that sort of thing. So Q4 is soldered back in place, so this is almost in the exact configuration as it was when it came in, apart from we have the speaker wires across the terminals, which we didn't have on first initial testing. So I'm going to power it up and see what it does. Let's go for full rail test here. Nothing yet. Ah, there we go, we have Class D switching. Huh, interesting. So we haven't actually changed or done any repairs really. All we've done is reflow Q4 basically and poke around and give it a little clean. Like I say, the only difference here is we do have our 16 ohms connected at the speaker terminals. Now, removing that shouldn't make a difference. Amplifiers should be able to come on and idle just fine with no load on the speaker terminals. It's not very healthy for a Class D amplifier to do that for long periods of time, especially not with signal playing, but they should absolutely still power up and idle. So I'm just going to do that with this now removed, just to see whether that still comes alive, because now it's in the exact configuration it was when it first came in. And yeah, absolutely fine. Still get Class D switching, everything operating as intended. These are slightly frustrating ones because I haven't really done anything. I haven't changed or found any bad component. I don't really know what has fixed that, other than the fact that it possibly was some slightly conductive carbonized soot that we've shifted as we've been poking around, or a very slightly bad solder joint on one of these parts over by the drive ICs that we were probing, and we've just kind of pushed up against the pad again when now it's working. So because these Taramps are a little bit known for having slightly not enough solder on especially these glass diodes, I've come across issues with that before, I'm going to go ahead and reflow and add some fresh solder to any parts that I was poking around with quite vigorously, just to make sure that we haven't got a poor solder joint that we've temporarily sorted by poking around. Give it a bit more of a clean up, and then I'll do sort of half an hour worth of testing with a speaker connected, and provided it passes that and continues to work fine, whatever we've done, we have sorted the issue. Slightly annoying because I can't say, oh yes, this was the issue, but sometimes the ghosts are playing games with us and we fix the problem without knowing how. Ah, alas, there is one last thing that I want to check that could have been the problem. See these output inductors? These are a bit wobbly here. So when this amplifier is mounted in a very bassy car with lots of vibrations, these can cause shorts in their winds and or to the board. So I just want to power this up. This is a little bit dangerous because we have going to have high voltage on these output inductors, and I'm going to give them a wiggle, and just in case one of them does have an intermittent short and causes the amplifier to go into protect. So I've reflowed everything, so this should just power up. I'm going to put the 16 ohms back in the terminals because it's a little safer like that. So let's power up once again. 9.4 volts, going to keep this nice and safe, keep the rail voltage nice and low. Let's go for a power up, make sure everything's okay here. There we go, powered up. So I'm just going to give these a wiggle, hopefully nothing goes bang. That seems alright. Seems alright as well. Yeah, so I don't think we have any vibration related issues here going on, because otherwise that would be sparking and it would be in protect by now. So, let's connect a speaker, let's do a little test. Test speaker is connected, so let's go for a little test. I'm going to stay at 9.2 volts for initially, and then I'm going to go up to 12 volts once I'm happy with its operation. So let's power up, do the health check mode. Okay, yep, there we go. Class D switching is initialized. Turn the signal up a little bit here. Definitely playing nicely. So yeah, going to increase to 12 volts now. Still working just fine. And finally 14 volts. Yeah. It's working absolutely fine. No problems there whatsoever. So the ghosts have got me this time, and I can't tell you exactly what was wrong with that amplifier. Hopefully it will retain operation for some time yet, but nonetheless I hope you enjoyed that, and I hope it was educational and you learned something about how to diagnose this kind of amplifier. It was kind of interesting, forcing the outputs into operation there. So until next time, stay safe and make it work.